Hello everyone. In this video we will discuss velocity and acceleration in fluid mechanics. When we study moving objects, there are two approaches of studying them. One is the Lagrangian approach, which is where we track individual particles or bodies or elements that are moving, and with time we try to study their location, velocity, acceleration, and all the other properties. That is, wherever a particle or a body is right now, after time t, where it will reach, what will be its velocity, what will be its orientation, shape, and so on. On the other hand, in Eulerian method, we study the motion of particles occurring through a given point in space. It may not always be a point. Instead of point, we generally choose a volume. It may be a small volume, it may be a considerably larger volume. So in that particular volume that we have chosen, what is happening to the particles that are moving into and out of that volume? That volume is also called control volume. Sometimes instead of a volume, we simply choose a cross-sectional area sometimes. Now try to understand why these two approaches are necessary. They're useful in different situations. For example, let us consider a river. So in this river, at one point, somebody or some factory, let's say, is dumping some pollutant or waste or something. So they have dumped some kind of waste in the river here, in this location. After some time, that waste will reach this location. So when we study it like that, that is, I have dumped it here, after 1 minute where it will reach, what will be its shape, how it will spread. So that kind of study is Lagrangian study. On the other hand, let's say somebody is pumping water from the river. So what he will be interested in is the purity of the river water. So he knows that somebody has dumped some kind of waste in the river. So while I am pumping water, extracting water from the river, I need to know what is the purity of the river. So from this time up to this time, I need to stop my pumping because otherwise I'll be taking in polluted water. So for that person, the concern is not how individual particles are moving, how the waste is moving. For him, the concern is when it is going to cross this point. So he will, at some point of time, he will see that, okay, the waste has reached this point. Now it will take this much time, suppose some amount of time, 1 minute. After 1 minute, the entire waste or the polluted water has crossed the point. So now I can again keep pumping water from the river. So that kind of method is the Eulerian method. Now, mathematically, how to deal with different quantities. In Lagrangian method, velocity is simply a function of time and is defined as rate of change of displacement of a particle. So velocity in x direction is u, that is dx by dt. In y direction it is v, dy by dt. And in z direction, let's say it is w, which is given by dz by dt. On the other hand, in Eulerian method, it is not a function of the location of the particle, but rather a location that we have chosen. That is, u is a function of the x, y, and z coordinates and time. Remember, these x, y, z coordinates are not the coordinates of the particle, it's just a fixed point in space. Instead of x, y, z, if we take x1, y1, and z1, which is a different point in space, then the velocity will be a different velocity. Similarly, v is a function of x, y, z, and t, again the w is a function of x, y, z and t. Now coming to acceleration. Acceleration in the x direction is just that differentiation of the x velocity, that is u. So it is given by d2x by dt2, and the acceleration in y direction is given by d2y by dt2, and so on. In Eulerian method, we can write it like this: ax is du by dt, ay is dv by dt, and so on. But the problem is, when I'm writing du by dt, we have to remember that u is not just a function of t. So although I have not written a partial derivative symbol here, I could write partial derivative. That would only mean that what is the rate of change of velocity at this particular point in space. But here we have written the complete derivative, not the partial derivative. So what would that mean? For that, we'll need to understand some new concept, which is called a material derivative. It is the time rate of change of quantity in space and time. While understanding acceleration, it is that quantity will be velocity. So that is time rate of change of velocity will be acceleration. But for now, let's try to understand with the help of any arbitrary quantity, c, suppose. So c is some function of space and time, that is x, y, z and time. So after a certain time t, what will be the change in this property c? C is the property, let's say, pressure or density or concentration of a certain kind of chemical in water in a given element. So dc will be given by the partial derivative of c with respect to time multiplied by the time elapsed, then the partial derivative of c with respect to x multiplied by a length dx. What is dx now? The dx is the distance traveled in time dt by this element of which we are concerned about the property c. Similarly, the partial derivative of c with respect to y multiplied by distance traveled in y direction, which is dy during time t, and partial derivative of c with respect to z multiplied by dz. Now if we write dc by dt, then we will get this kind of an equation. And as you can see here, in the first term, this dt by dt is obviously 1. In the second term, dx by dt is velocity of the element in Lagrangian form, not in Eulerian form. Similarly, in this term, dy by dt is the Lagrangian velocity in the y direction, and dz by dt is Lagrangian velocity in the z direction. That is, now we can write it is partial derivative of c with respect to time, then del c by del x multiplied by u, del c by del y multiplied by v, del c by del z multiplied by w. Just to write it in the conventional sense, where we do not write a function after the partial derivative or the derivative. So let's write it this way. Now, instead of c, if we replace c with velocity, let's say velocity in the x direction, which is u, then acceleration in x direction will be given by du by dt, which is the complete derivative, not the partial derivative. So du by dt is, in a similar fashion, we can write it like this. And similarly, acceleration in y direction can be written like this, and in z direction it can be written like this. Now let's try to understand the meaning of the different terms in this equation. So this is the equation for acceleration. Du by dt is del u by del t, which is the partial derivative of the velocity with respect to time, not with respect to space. That means at a given point in space where x, y, z are not changing, that is, it is a fixed point. Here, with time, if the velocity is changing, then that rate of change of velocity is given by this del u by del t, or partial derivative of u with respect to time. This is called local acceleration. Now, the other three terms, they represent the acceleration of a particle as it moves in space. The first term, that is u into del u by del x, as we have discussed in the previous two slides, it is the rate of change of this velocity as it moves through a distance dx. Similarly, the third term, v into du by dy, is the rate of change of u as it has traveled through space in the y direction by a distance dy. Similarly for the fourth term, last term. So these terms together is called the convective acceleration. Now, local acceleration, as we have already mentioned, is acceleration at a fixed point in space. In case of steady flow, since things are not changing with respect to time, therefore, in steady flow, local acceleration becomes zero. On the other hand, convective acceleration, it is the acceleration of a fluid element as it moves through space. In uniform flow, in this case, the convective acceleration is zero, because as fluid moves through space, there is no change in velocity or any other property in case of uniform flow. Let's try to understand this with some examples. Let us consider a pipe fitted with a valve, say. Now, here at this point, there is some velocity of fluid. If we consider another point here, since the pipe is prismatic, its cross-section is same throughout its length, so here also the velocity will be same. Now, if I'm opening the pipe a little bit, then the velocity will increase at this point. So while I'm opening it, velocity will increase with time at this point. So that is given by del u by del t, which is the local acceleration. This same thing will happen at this point as well. Here also the local acceleration will be del u by del t. So that is the example where we can say that we can have an example of local acceleration. Now, in this case, let us consider a pipe of varying diameter. So here, as liquid moves along this direction, its velocity has to increase because the cross-section is smaller in this direction, so velocity is increasing. Now, if the flow is steady, if we are concentrating on this point only, then the velocity is not changing at this point. But as the liquid moves to this point, its velocity is increasing. So in that case, velocity increase, or the rate of change of velocity, will be given by the convective acceleration. Now, it's a different problem whether you consider this one-dimensional, two-dimensional, or three-dimensional. If we consider this to be one-dimensional problem, then we are only concerned with the velocity u, suppose. So u will change you will increase in this case with the x direction as we move in the positive x direction. Now, if we consider a pipe, a variable diameter pipe fitted with a valve where flow is taking place, it's accelerating towards this direction, and in that, if I am opening the valve a little bit, then there is local acceleration at this point and at this point. At the same time, there is convective acceleration throughout the pipe. So this way we try to represent velocity and acceleration in fluid mechanics. Now we'll discuss in subsequent lectures how to do some mathematical analysis of this kind of flow parameters, flow phenomenon, using the acceleration and velocity equations that we have discussed here. So for now, that's all for this video. Thank you for watching.